Look up at the night sky, filled with billions of stars. For centuries, humanity has asked one fundamental question. Why is our universe exactly the way it is? Why do the laws of physics perfectly support life? A slight alteration in gravity would destroy everything. If the strong nuclear force changed, atoms would collapse. Scientists call this the fine-tuning problem. It seems as if the cosmos was tailored for us. But nature rarely relies on pure, accidental luck. In biology, complex designs emerge through evolution. Charles Darwin showed us how life adapts over time. Could the same principle apply to the entire cosmos? What if the universe itself is an evolving organism? This is not science fiction. It is theoretical physics. Welcome to the theory of cosmological natural selection, a concept that redefines everything we know about existence. To understand this, we must look at black holes. Black holes are the most extreme objects in space. They form when massive stars collapse under their own weight. At the center lies a point called the singularity. Here, density becomes infinite, and space-time stops. For decades, physics has struggled to explain this point. General relativity and quantum mechanics clash here. But what if a singularity is not an end? What if it is actually a brand new beginning? Physicist Smolin proposed a revolutionary idea. He suggested that a black hole creates a new universe. As matter collapses into the singularity, it bounces back. This bounce initiates a new Big Bang on the other side. But this new universe is hidden from our view. It exists in a completely separate space-time metric. This means our own universe might have a parent. If universes can reproduce, a mechanism must exist. Smolin suggested that laws of physics are passed down. When a new universe is born, it inherits constants. These include the speed of light and gravitational strength. But the inheritance is not perfectly identical every time. Small quantum fluctuations cause minor mutations in the laws. Just like genetic mutations in biological organisms, most mutations result in minor shifts in parameters. Some shifts make the new universe unstable. If gravity is too strong, the universe collapses instantly. If gravity is too weak, no stars can ever form. These dead universes leave no offspring behind. But what happens if a mutation is successful? A successful universe is one that creates many black holes, because more black holes mean more opportunities to reproduce. This leads to a cosmic version of natural selection. Universes with high black hole production proliferate. Over deep time, the multiverse becomes dominated by them. Let us examine the state of our own universe. Our cosmos is exceptionally good at forming black holes. It contains trillions of them, across billions of galaxies. This is because our physical laws favor star formation. Carbon, oxygen, and hydrogen are abundant everywhere. These are the exact ingredients needed for massive stars. And massive stars are the precursors to black holes. This correlation is the core evidence for Smolin's theory. The universe is optimized for black hole reproduction. But there is a profound, beautiful coincidence here. The exact conditions needed to create massive stars are also the exact conditions required for life. To make stars, you need heavy elements like carbon. To make life, you also need carbon as a foundation. Life is not an accidental miracle in a cold cosmos. Life is a natural byproduct of a highly fertile universe. Think of our universe as a single tree in a forest. A tree produces seeds to ensure its lineage continues. Every black hole is a seed dropped into the dark. Most seeds fall into fertile ground and grow. This creates an endless web of multi-generational space. This hypothesis is known as the fecund universes theory. It shifts our perspective from mechanics to biology. The cosmos is not a cold, dead clockwork machine. It is a dynamic, self-perpetuating ecosystem. This elegant model solves the fine-tuning riddle. We do not need to invoke infinite random multiverse. We only need to understand the power of selection. The laws of physics are fine-tuned because the bad ones died. Only the most reproductive variations survived the test. We live in a universe built on cosmic inheritance, an unbroken chain of cosmic birth stretching back forever. This concept forces us to rethink our place. We are not anomalies in a hostile environment. We are part of the cosmic reproductive cycle. Our presence is deeply linked to the laws of stars. If Smolin is correct, the multiverse is alive. It is a vast arena of competing physical parameters. And our universe is one of the grand champions. It has mastered the art of creating black holes, and by doing so, it guaranteed the rise of life. This theory remains a hypothesis for now. We cannot yet peer inside a black hole to check. We cannot measure the laws of a baby universe. But it offers a beautiful bridge between sciences. It unites the vast scale of general relativity with the microscopic world of quantum mechanics and the adaptive power of evolutionary biology. It suggests that order can arise without design, that complexity can grow from simple physical rules. The cosmos is a self-organizing masterpiece. Next time you look up at the stars, remember that you are looking at a living lineage, a universe that found a way to survive and multiply.